Sadeghi?
That's good.
Okay,
Yeah.
all right.
Yeah.
So he received his PhD from University of British Columbia in Canada and did a postdoc with University of Toronto and then joined the industry for a couple of years. And then he joined the University of Alabama in Huntsville and then being the faculty over there. So he has more than 100 peer-reviewed journal publications and one patent. So today he's going to talk about material design for control of spontaneous emission of semiconductor compounds. Let's welcome our speaker.
Thank you very much. Thank you for the invitation, Professor Wu. I enjoy the campus very much. We have good lunch with some of the students and really nice campus here. Weather was very good, much better than Huntsville right now. So it's a kind of good time to discuss. Thank you for attending in this talk as well. So what I'm going to talk about is a little bit touch on some of the research that we do. And the topic today is about how you can change the spontaneous emission of semiconductor. Of course, when I say spontaneous emission, everybody knows what is that, and that's a good part of it. That any textbook a very long time ago, we heard about a spontaneous emission, which basically is that if you have an atom or anything, you're excited, after a while, it's going to come back. And it's going to come back after a little bit time, depends on what you have. And so this is kind of classic the definition of a spontaneous emission. What I'm going to talk about is that how we can manipulate the environment to enhance that. Again, this is by itself is not a dramatically new subject of research, because all of you know from the Fermi golden rule that, well, if you have rate of transition, which is this, of course, this is the material part, but this is the photonic part of it. So basically what happens is that if you change the environment, means that density of photon changes, you can change the rate of the spontaneous emission. You can make it slower or you can make it fast, depend on how do you change the environment. So in these cases, for example, some people use a dielectric cavity. So what do, you put atom somewhere you want, and you put different layers right on the bottom and the top. And what's happened is that you generate cavity. Depending where you put your atom, either you can enhance that, or you can reduce the rate of spontaneous emission. Yes?
So what is the H in there in the matrix element?
What is the, I'm sorry?
H.
H is a Hamiltonian.
If it's a Hamiltonian, then this matrix element is zero if these are two different eigenstates of the Hamiltonian.
No, F is, they are not zero, because what happens is that I is the initial value, is the interaction between the two. For example, a dipole.
Wait. If I is the initial eigenenergy state, F is another, in final eigenenergy state. They are both the eigenstate of the H, right?
They
They
are
are
both.
eigenstate of the H.
No, they are not. No, that. H is the double electric field. I is
No, H is a Hamiltonian,
Well,
debating part of it.
so it cannot be the Hamiltonian itself.
well, it is interaction part of it.
Okay.
You know,
It's
if you
interaction Hamiltonian.
interaction part of it, it's a dipole. For example, E times R, which has it has odd.
It's fine.
Okay, so but then.
But this is very easy to be confused with.
Oh yeah, you are absolutely right. I probably should put V or something there that it tells you it is just interaction. Interaction, because if it is basically parity is.
No, H sub I usually, or delta H.
Okay. Okay. Yeah, absolutely. You want to keep track of parity. Make sure you don't go from same parity. So it actually is non-zero. So it is dipole. It is E times R, and it has a odd parity. I has even parity. F has odd parity. So the combination is non-zero. So then what you have over there is rho, which is density of a state, and you can manipulate density of a state either with as a this, and the other way to do that, instead of dielectric, people use metallic nanoparticle. Metallic structure, not necessarily nanoparticle. So what happens is that when you put metal close to each other, and as I talk about that, even they are by themselves, when you excite them with the light, what happens is that you generate plasmon. Plasmon generate quite an amount of near field, and it has concentration of the field there. And if you put quantum dot or any quantum emitter close to that, then you will start to have enhancement of emission. So this is the work of other, for example, you have bow tie, or if you have a metal and another metal and put it close to each other, you generate quite amount of field enhancement, so you can have a spontaneous emission.
In this case, basically your eigenstate, so you band the band structure actually is changed.
Band structure of the quantum dot?
The state is dependent on the material band.
That's correct. That's correct.
So in this case, actually you alter the band structure.
Well, that's a good point. You can do or you cannot do, depending on the intensity of the field that you have. Even a little bit enhancement of the field, so 2 times, 3 times enhancement of that, you can actually enhance the spontaneous emission. But you are absolutely right. If you go to the high field regime, the whole thing, the band structure is going to change as well. But again, the spontaneous emission is going to increase as well because of the immense amount of field that the quantum dot experiences. So what happens is that when we talk about metallic nanoparticle, and the story is that metal have quite amount of free particle. So if you send the light, and if they are small enough, if you send the light, the light is able to let the free electron oscillate. And it acts as an oscillator too, in the sense that it has a certain frequency, which at that frequency it oscillates. And that is called plasmon resonance. The whole thing is called localized surface plasmon. If you make it large, then what's happened is that then you can have, instead of dipole, you can have multipolar plasmonic effect. This is our own simple COMSOL calculation of metallic nanorod gold that you can have. And then if you do array of it, then you can combine photonic and plasmonics together. And then over there, then like the grating that you have Rayleigh, you have then like any periodic structure, and then plasmon get coupled together and generate new plasmonic structure, but it is photonic plasmonic structure. And sometimes those are extremely sharper than the plasmonic peak itself. So it's called surface plasmon resonance. And you can see that it actually fills quite much the space between the nanoparticle. These are due to the coupling with the photonic structure of your periodic structure. And plasmonics has quite an amount of application. I mean, I probably don't need to emphasize on it. It goes all the way from sensor, sub-wavelength, waveguides, and making imagery, drug delivery, quite an amount of research that how people use metallic nanoparticle for drug delivery. Hot electron technology. So basically, the simple, modest, well-known Schottky barrier that people know about that quite much can be the source of harvesting hot carrier from metal. So basically you have the metal, and when you excite that, you basically, we know that it get absorbed and gives you heat. Ultimately it ends up with heat. But before it gets to end up giving you heat, it generates plasmon, and plasmon decay give us energy to electron. Electron is very high energetic, and if you have a Schottky barrier, you can capture that electron into your semiconductor area, doesn't let it to go and becomes heat. And then you can use that hot electron for what you want. For example, how about infrared detector based on metal, or photovoltaic devices, or photocatalytic devices? You can use that hot electron for those many applications. Or if you want to make it fancy enough, you can make metal material, this is not my field. You can find the internet. I don't see this is possible that you can see through people, but it is hope that people can use it to do this kind of thing. But for light harvesting is quite applicable. But again, this is not the whole story. Imagine that if I have pick up one metallic nanoparticle and a single quantum dot close to each other. I show it to you here our result for theoretical work. I wish it was experimental, that we were much more happier, but it is experiment. Not that experiment is bad, but I wish we could try that. But anyway, so this is a metal nanorod, and is a quantum dot here, and this is a more or less similar metallic nanorod and quantum dot there, right? We studied, and I don't want to go to the detail of it. After this, I would be happy to go in detail, just giving you some glimpse of what you can do. We showed that this structure can actually act as an AND logic gate. The dimension is about 20, 30 nanometer along that. And you can see that if you send two lasers to it, one mid-infrared and the other visible, you can set it up that you can have enhancement around the metallic nanoparticle when both of them exist. If one of them come at the one time, you don't get that. Or, against another interesting subject, is that all of us know the when you have a metallic nanoparticle, the plasmon decay by about 20, 30 femtosecond, and quantum dot decay by about 500, 400 femtosecond. We studied this, and we showed that under certain condition, you can send two CW pulse, means that the amplitude of the pulses, CW wave, light, not pulse. You can send two CW, means the amplitude doesn't change, continuous wave laser to it, and then you can see that the field, near field plasmonic field of the metal start to oscillate by itself. So this oscillation is not, this is oscillation of the intensity, remember, it's not the natural wave that it oscillates, and that would be the phase. This is the oscillation of the intensity. So actually the amplitude goes down and up, not the, so that's this interesting thing that you can do that. So it actually acts as a kind of oscillator. So these are the kind of touch on some of the theoretical work that we are doing. But in the experimental part, which is focuses on what I'm going to talk today, is about plasmonic fluorescence enhancement. And that is to say that if you have metallic nanoparticle, like you can make it in different forms, I mean, anywhere you want, nanodisk, rod, nanodisk small, and nano island. This is very simple to make. And you make it, you put some dielectric on the top and put quantum dot structure on the top. So if you do that, you can see significant change in emission of the quantum dot. So let me show you. This red line is the emission of the quantum dot right on the glass. And then the blue line is the emission of the quantum dot which is on this structure. And they are side by side and they are very tiny. And what happens is that you can see that emission of the quantum dot on metallic structure is about, I don't know, 10 times at least larger than the emission of the quantum dot on glass. The question is that why it becomes larger is not that you generate more energy in the quantum dot. No, the quantum dot absorb. The fact is that the near field of plasmon enhances spontaneous emission that I mentioned to you earlier on. As the spontaneous emission becomes more efficient, it can better compete with the non-radiative decay of the quantum dot. So that's why the non-radiative decay cannot bring down the emission of the quantum dot as much as in this case. Here, you have to remember a quantum dot as it emits when you excite it, you have to deal with the fact that the quantum dot, the exciton that is generated, electron hole that is generated, can be grabbed by defect and gone, or they can end up with the radiation that you like to get. So these two always are competing with each other. So if you want to enhance emission, and you cannot do much about the defect, but if you enhance the radiative decay, then you have more emission. And that's what's happening here, the reason for having enhancement of emission. So the question is that how we can design the environment to promote radiative emission. But again, not just repeating what other papers have done before. And that is, like the one that I showed before, enhancement of emission because of the plasmonic effect or cavity effect. What you can do, how you can design the environment and to enhance it. So what I'm going to talk about is that first is about that at the level of ensemble of quantum dot, many quantum dot close to each other. Then what I do, I go to the limit of single quantum dot. When they become single quantum dot, the rules a little bit changes. Probably you heard about quantum dot blinking or fluorescence blinking of the quantum dot. The question is that how we can control that blinking. And as I showed to you, by changing the material, you can pretty much change it quite dramatically. And then I go towards application of exciton-plasmon coupling to control intensity and polarization of emission of the quantum dot. So, this is, you saw this slide before. I showed it in the couple of slides, maybe 2 slides before. If you ask how I can improve this, how I can enhance that emission, and of course, as I said, if you deal with the defect, reduce the defect. But if you don't, you want to design your material to do that, you have to consider 2 facts. The first fact is about, as I said, that is enhancement factor, field enhancement factor that I mentioned that. But the other one, which is kind of playing negative, but it happens very naturally, is the fact that if you put a quantum dot close to a metallic nanoparticle, why the metallic quantum dot enjoy the high field, intense field of the metal, I'm afraid it actually gives up some of its energy to metal. And that happens through FRET, or Forster Resonance Energy Transfer, which is common. Even if you go out, walk through the, here, look at some of the photosynthesis material like leaves or so, there is a good amount of discussion that actually FRET happens there too, in one form or the other. So these are the two competing processes. This is you don't want it because it actually removes the energy, gives up heat. But the top one, you want it because it enhances the spontaneous emission. So the traditional way to look at this is that you just go adjust it. So let me explain a little bit about FRET. FRET process is basically resonance, transfer of energy without photon. So if you have two quantum dots close to each other, very close to each other, there is a chance that energy go from a smaller quantum dot to larger quantum dot without exchanging electron, without exchanging hole, or without exchanging the photon. Basically what's happening is that one quantum dot as a dipole radiate, start to oscillate, and the other one start to grab it, and energy goes from one to the other one. This is FRET, and it is very common. And it is very much used for sensor application here. For example, you can, if you have a dye here, biological application, for example, and a biomolecule in the middle, and your quantum dot here, so if you send the light to it, the light goes towards this, get absorbed to the dye, and gives you red. So mostly what you see in your sample is the red light. So you know that this biologically kind of interface attach the dye to the quantum dot. Now, if you introduce some biological molecule which can kind of separate these two from each other, has interaction with this protein substrate, for example, disintegrate that, separate them, then dye goes its own way, gets separated from the quantum dot. So if you send the light to the system, you basically get emission of the quantum dot, which is green. So basically, if you see red, you say, well, you don't have this biologically molecule that attach this. If you see green, you say that, well, already interaction happened and they get separated from each other. And the fact is that quantum dots are very, very good absorber and give up emission very nicely. Even I will show you in a slide, couple of slides later, you can see one of them. And you see that how much bright they are. So what we do is that to show this, so you start from a substrate, regular substrate, simple, modest, and put gold, but you have to make sure gold is rough. It shouldn't be smooth. And then you put silicon on the top and quantum dot on the top. And then what happens is that we adjust the distance between these two and look at the lifetime of the quantum dot, as simple as it is. And this is the setup, very simple. Laser come, hit the quantum dot, and we grab the emission of the quantum dot into the spectrometer or lifetime measurement. And these are the results that we obtain. This is nothing new. Everybody knows that. Here is the deal. When the thickness of the silicon, this is the silica, when the thickness of silica is about 5 nanometer, this is the emission of the quantum dot on the silica, and this is emission of the quantum dot on the silica and gold. And you can see that you don't have actually enhancement. You have much less emission. This is because energy of the quantum dot, you have good amount of field enhancement, but the emission of the quantum dot goes very efficiently towards metallic nanoparticle. And if you look at the lifetime, This is the lifetime of the quantum dot on glass, and this is the lifetime of the quantum dot on glass, and underneath of it, gold. You can see that how fast it decays. Now, if you increase the thickness of the gold, silicon oxide to 15, emission becomes fairly equal. So emission on the glass and emission on the glass and metallic nanoparticle become fairly same. But then again, you see that the emission, the light on the glass and gold decay faster, number 2. But the emissions are similar. But then if you increase it to 25, you can see the emission of the quantum dot on the gold increases compared without the gold, 25. And that's why, but still this is faster. Emission of the quantum dot on the gold and glass faster than on the glass. So this is happening. And you can play around, and that enhancement in terms of, instead of 3 can become, like the previous slide, can become 20. Some people talk about 100 times enhancement. So as you increase the thickness of the silicon, you reduce Forster energy transfer, but keep some of the field enhancement, and that's the reason for emission enhancement. So you go from suppression of emission to enhancement of emission, and this is the lifetime of those. All the time, emission of the quantum dot, although intensity is higher on the metal, but it is long. You can see it's about 10 nanoseconds. If you talk with many people in the device, they don't like 10 nanoseconds because 10 nanoseconds is very long. People like to go shorter, and they make very complex structure to make it shorter and shorter. So what I'm going to show here is that we play around with this and make the lifetime much shorter by 1 orders of magnitude shorter, but the emission does not change. So we deliver the same amount of intensity, but we make the lifetime extremely short. So here is what we have done. We start with a substrate and a gold. This is a thick gold, which is generate good amount of field enhancement. And this kind of purple color that you see is kind of illustration of how the field goes, how far it goes, and influence the quantum dot. Then in the middle, instead of we put silicon oxide, we put amorphous silicon with a sputter. On the top of that, we put a very tiny layer of gold, and it is maybe about 0.5 nanometer gold. So 0.5 nanometer gold, it doesn't generate large metallic nanoparticles. It makes very tiny, small nanoparticle. And so later I explain why, but let me tell you what we got. So we put quantum dot on the top, and this is what we got. So if you look at the spectrum number 1, is the emission of the quantum dot on glass, on amorphous silicon, just silicon. And it has some number. If you do not have the thick layer of gold, which is this one, and you put directly on silicon without this gold, then you get number 2. But then if you have the gold back, if you have the gold and there's everything together, you get number 3. We get sometimes upper or lower. So emission of the quantum dot on silicon, gold, silicon, and 0.5 nanometer of gold, they become kind of similar. But then look at the lifetime. This number 1 is the lifetime of quantum dot on silicon. And you can see, well, again, it's about maybe 5-6 nanometer. Actually, I write it here, 4.6 nanosecond. But then this the line that you see, the dark, I guess, is kind of blue color or dark color. You see, hardly can be seen, is the emission of the quantum dot, lifetime of the quantum dot, number 3. They have the same intensity. But the amount of lifetime of the quantum dot on this structure is about 430 picosecond, but the lifetime of the quantum dot on silicon by itself is about 4.5 nanosecond. So what you did, you reduced significantly the lifetime of the quantum dot, but then you get the similar amount of light out of it. Why it is useful? Well, if you think about, yes?
Is the first picture obtained by continuous wave excitation or pulse excitation?
Oh, that's a good point. The first one is obtained by continuous. Yes. So what happens is that the message is this one, that you get the same amount of intensity, but you get much faster. And the faster, the better. If you think about device application, this, you want to faster. People like to make it to maybe 40 picosecond. You can do it, but there is some level of complication there. But this is the simplicity of that, is that we just put it there and put the objective there, and we collect the light as easy, simple. But if you want, I want to talk about the reason behind that. You can, here I show the SEM images of different thickness of gold on silicon. And you can see that if it is 0.5 nanometer, you can see some little island. You see this is 200 nanometer. They are tiny island packed together. But then if 2 nanometer, it becomes like this. 4 nanometer is this, and this is 40 nanometer, which is the lower, thicker substrate that we have. The deal is this. When the metallic nanoparticles are very, very tiny, as the case of 0.5 nanometer, they actually act as a frit center. And you can see it here. You see, this is the extinction of this. And you can see it has a peak about 610 or 20. This is plasmonic peak. And it is right at the wavelength of the quantum dot. So when the quantum dot are excited, right there, they deliver the energy to the metallic nanoparticle very fast. But then as you increase the thickness of it, it is 40 nanometer. Even we cannot measure that much, how much extinction we have, because 40 nanometer gold absorb much light. But if you look at the dark field of the light coming from the top, you see that there is nothing here. So there is no field enhancement. But here you can see a very strong peak, and it kind of suggests you that 40 nanometer of gold provide you a good amount of field enhancement. So what we did, we kind of play around with the balance between frit and field enhancement to our advantage. Okay, so now I go for my second part, how we can use material to play with the emission of the single quantum dot. You know, single quantum dot, we know they are very good, they illuminate very nice, give you lots of good amount of emission, but there is devil behind that. If you go to low single quantum dot level, the emission is not continuous, although you illuminate that with the CW laser. So if you have CW laser, you send the light, they blink. People work a lot to reduce that, but in many cases that we have, it blinks. So this is the one of our measurement. So we hear what you see some of the dots come and go here. If you look at carefully, even some become dark, and then later, after a while, they are coming back. So this is blinking of what we did. Basically, we bought semiconductor quantum dot. we put in toluene so much, so such that with spin coat that they are far, far from each other. They don't see each other anymore. And then we put it in front of EMCCD camera, which is quite sensitive camera. It is maybe minus 80 Celsius cooling. And then when you do that, you can see single quantum dot. And you see any of the dots that you see here is single. And some of them less brightening, some of them blinking fast, some of them don't. It is a hard question to answer, even why they're blinking coming, then telling you why some of them are blinking more, some of them less. There's lots of things to argue. But if you have quite amount of quantum dot, ensemble, lots of other quantum dot, the emission is continuous. This is an image of single quantum dot again. You can see that it's quite bright, you can see them. And this is the blinking that happens. You can find it anywhere you want. I mean, there are plenty of them all around. So if you ask where is coming from, why we have single quantum dot blinking, well, the common theory behind that is that if you have a quantum dot and you continuously excite it with the laser, so you don't turn off and on your laser, so sometimes it becomes dark, although you continue to excite it. Why it becomes dark? Because the idea is about the Auger recombination. So when you have one electron, one hole, you basically have a bright state. So the decay. But if either temperature is high enough, some of the electron can go right, get trapped in the trap state, which plenty of them are available in normal quantum dot, get trapped. As gets trapped, then there is one only carrier there. So if you excite that with another photon, you generate one electron, one hole, then you get Auger recombination. And then the fact is that that carrier, it is believed, is coming back, and then quantum dot becomes bright again. So this is two cases. You have two electrons, two holes. One get recombined, but instead of giving you photon, it takes that electron and put it in the other, in the darker state, in the defect state, and this becomes dark. Or it gives off energy, just put it in upper level. But this is no Auger recombination. There is Auger, but there is no defect. But this is defect that people believe is responsible for blinking that you see. You see, in this diagram which I showed to you, if you carefully look at that, it is kind of advantage to having that process. For the people who are interested in quantum computation, optical, and they are interested in single photon emission, not two photon. You want two photon comes one after the other, not two photon, one photon at a time. Quantum dot, this type of colloidal quantum dot, is actually the bliss. Because what happens is that you have here two exciton. You can have multi-exciton recombination, but that process reduces to one. You see that? This goes there, one goes up and one carrier left, and it is good for you to get single photon emission. You suppress multi-exciton emission. So this is the work of others, and you can see that you can suppress, if you put it gold close to metallic nanoparticle, so this is blinking in the absence of metallic nanoparticle, and this is blinking in the presence of metallic nanoparticles. So the common idea is that metallic nanoparticles suppress blinking. And the reason that metallic nanoparticles suppress blinking is because field enhancement enhances radiative decay. Radiative decay can become so competitive with the Auger recombination that doesn't allow Auger recombination happen so much. So that's the reason that it reduces and you have less. This is a kind of idea behind of having metallic nanoparticle reducing the blinking. So you go from here to there, from here to there. But what we did, we actually try to control single quantum dot emission. For that, we use a structure which contains, again, silicon, gold under silicon, silicon and aluminum oxide, and gold, silicon, aluminum. So all layer on the top of each other. And then we went from different regime, from many quantum dot, which is you have ensemble of quantum dot, a step by step down to the case that you have single quantum dot, and see what's happened. I have to go a little bit fast, but here you can see that this is decay of quantum dot on silicon. As you can see that N1 is ensemble of quantum dot, many quantum dot, N4 single quantum dot limit. So remember, N1 many quantum dot, N4 single quantum dot. You can see that emission of the quantum dot when it is ensemble is lasting longer than emission of the single quantum dot. Single quantum dot decay very fast. Of course, the reason behind that is that if you have ensemble of quantum dot, before quantum dot gets trapped into the defects of the silicon, it goes to other quantum dot. And it gives you light chance to emit light, so you can collect light before you're losing the electron hole. But if you make single quantum dot, instantly when you generate the light, it gives off its energy, goes into, because of the carrier goes to the substrate, and the light goes off. You don't have, it is very fast. Then, if you go for with the gold, and you can see everything becomes faster. Every one of them is become faster. But the reason it becomes one of the faster because Forster kind of taking care of the quantum dot on the top have the chance giving up the energy to the metallic nanoparticle too. So that's why it makes it faster. So I a little bit make it short because I want to touch the other subject. But let me show this, what I was going to talk about is important. And this is taking image of the sample. So this is N1, this is concentration, high concentration of the quantum dot, a little bit low, and N4 is a single quantum dot regime. And those circles that you see, these are sampling point. We put the light detector at that point, and we collect the emission from that point over a period of time. And this is what we obtain. So you see, if I walk across here, all of them is on silicon. But ensemble of quantum dot, less, and less. You can see that blinking happen when I'm at N4, which are supposed to have single quantum dot, and this is the case. But the beauty of that is that if you look at this one, which is gold and silicon, remember the previous slide, I showed that silicon, gold is supposed to suppress blinking. But if you look here, I go from here, high density of quantum dot, no blinking. But if I come to N2, which I didn't see any blinking here, I can see distinct blinking happening here. And if I walk, I have more blinking, and even the patterns of blinking changes. So if I go with, for example, gold, silicon, and aluminum oxide, you see that again, I get blinking at the concentration which we were not supposed to get blinking. The concentration that's supposed to give us blinking is this one, which all of them shows the blinking. And then by introduction of aluminum oxide, you can change the pattern of the blinking. And the reason behind that, it goes to the fact that silicon is full of defect. Amorphous silicon that we use is full of defect. Gold underneath generate plasmonic field enhancement. If you didn't have silicon, gold enhances the radiative decay so much that Auger combination that was responsible for that couldn't happen that much. Blinking was suppressed. But if you introduce silicon, just simple live 15 nanometer of silicon, silicon is source of defect. And this result suggests that when you excite quantum dot, carrier goes to the defect side of the silicon. But the strange thing that we are working on it, and we are puzzled by that, this result suggests that they are coming back. Because it is bright, becomes dark, and then bright, dark, bright, and longer time of darkness and coming back. The fact that light comes back and forth, it may suggest that there is a possibility that the quantum dot in the presence of the silicon becomes neutralized, either by returning back. One option is that the carrier may return back. We are working on it. But the result that you see here, it suggests that you can change plenty the pattern of blinking based on the material that you put underneath. You can promote blinking if you use defect other than defect of the quantum dot itself. Okay, I have 10 minutes to talk, and I'm not going to miss that part. So it is interesting to me. Maybe some of you may be either theoretician or experimentalist. What I'm going to talk is what happens. Well, I'm talking about exciton-plasmon coupling. And this is, again, experimental. This is not theory. So don't get, well, if I see this before, I showed this just for kind of a metallic nanorod and quantum dot to show you some concept that I'm going to talk about that. But here I'm talking about exciton-plasmon coupling. So what happens is that if you have a nanorod, you have plasmon. If you have a quantum dot, you have exciton. And there are lots of literature talking about if you put them close to each other, they get coupled to each other. Even the coupling can be so strong that it degenerates the state of the quantum dot. It generates plexicon. They talk about that. There are lots of theory behind that. But here I talk about the type of exciton-plasmonic coupling that is not generated by laser, the plasmon that is not generated by laser, but the quantum dot. So here is the story. This is the quantum dot transition states. This is the plasmon, kind of picture, cartoon of it, a schematic of it. What we did, we send a light that excites only the quantum dot, not the metallic nanoparticle, quantum dot. What happens is that relaxation happens, and you have two chances. One chance is that quantum dot can give up its energy through the freight, and this heats up. The other one is that quantum dot can generate a field that excites the plasmon, and plasmon in return excites the quantum dot again. This is quantum dot induced exciton-plasmon coupling. So now, what happens is that this is the metallic structure that we use, a kind of array of metallic nanorod, simple. But you have to remember, we call this x-axis, and this is y-axis, right? Laser is coming. It doesn't matter what kind of polarization it has, because it gets absorbed in the quantum dot far from the band gap of it. And this is the structure. We have silicon with glass and quantum dot on the top. This is extinction spectra of the metallic structure. You see that the quantum dot decay at 650. Laser comes at 540. And there is a peak here, which I mentioned it to you, but it is not effective here. It's called SLR, surface lattice resonance, which is not playing much role here. But now, let's look at the emission that is coming out from the quantum dot. Okay, so if you look at this slide, the dashed line is the emission of the quantum dot that is coming from similar structure as here, but there is no metallic nanoparticle underneath. So coming from quantum dot on silicon underneath glass. And before light goes to the spectrometer, we put an analyzer. So we know polarization of it also. We analyze the polarization. And you can see that the light that is coming out from the quantum dot is not polarized. Quantum dot itself, in the absence of any metallic nanoparticle, it is not polarized. It is quantum dot, it kind of have spherical symmetry, it is not quantum rod or anything, so there is no preferred polarization for it, and this shows that. Now, look at the emission of the quantum dot that happens on the top of the, when there is metallic nanoparticle underneath. And this is the first thing that you see, wow, emission is much, much more. But the more interesting part of it is that the emission is much more only along one particular axis. And that axis is the same axis as y-axis. Remember that I mentioned y? So most of the light that is coming out is polarized along that particular axis, and the degree of polarization is immense. Remember, so this is normalized. So you can see that it is 0.6 to 1, 40% more light coming with the polarization along the short axis of metallic nanoparticle. If you divide it by each other, just give you the sense of how much enhancement you have. You have 11 times when the polarization is along x-axis, but if you look at the polarization along y-axis, it goes about 19 times. So the quantum dot emits with preferred polarization. And the reason behind that is that quantum dot can actually excite that particular plasmon mode. If you look at this figure again, along y-axis, there is not much going on. The plasmonic is very weak. But along x-axis, that one. Y-axis, you have pretty amount strong plasmonic field. So the quantum dot can couple with metallic nanoparticle, and that there is enhancement happen through the exciton-plasmonic coupling, but not exciton-plasmonic coupling that is generated by laser, but generated by the quantum dot itself. So to conclude that, actually, what I was looking to talk about is that how you can use the material property to change not only the emission of the quantum dot, polarization of it, and dynamics of it. And so the defect plays a crucial role. Sometimes you want to avoid that, but if you cannot, I mean, there are something that you can deepen your understanding, for example, regarding blinking or so, that you can do that. Exciton-plasmon coupling is a major issue. We are now putting good amount of energy to improve the system, improve the degree of polarization of the light that is coming, enhancing emission dramatically. Finally, of course, I have to mention it right at the beginning. This work was not possible, actually. This work was not possible without my student, where I can look at the whole thing. Here?
Next. Oh, that one, yes.
I forgot to mention that. Okay, yeah. Whalin and Ritwik, these two students, special Whalin planned special time for it. I mean, good amount of time. And this board, of course, I have to acknowledge support from NSF and UAH as well. Thank you.
So, any questions, comments?
So you've not talked about how the distance really play yet. So I assume that you probably try to make it very close by controlling just the layer thickness, right? So have you guys studied like when you change the thickness of this spacing layer, how quantitatively this coupling really changes?
That's a good point. What we did, basically to a start, we are working on it, but we start with the space that we know before. 15 nanometer, we know it before, optimize that to get a little bit decent enhancement. But spacing is something that we are working on it. That's absolutely a major parameter. In fact, we actually work on it in the sense of rough metallic nanoparticle spacing and quantum dot, we changed that. But for this one, which is nanorod, we still have not go down from 5 nanometer or less all the way to up to see how we can enhance that. That's something that we are working on. Absolutely.
I have two questions. The first one is, has anyone calculated the dependence of density state of quantum dot as function of the gold, the thickness of gold? So you basically, your conclusion is the enhancement of radiation of quantum dot is because you have the metallic nanoparticle on the bottom.
That's correct.
So basically that gives you the transition
That's right.
rate increase due to the increase of density state. Did anyone calculate that?
That I don't know.
But I would be surprised if nobody have calculated that how, if you have a metallic nanoparticle, and what we know, we can calculate field enhancement. For example, if you go to the oh yeah, it is a COMSOL simulation. We didn't but I am surprised that nobody have calculated that. You can easily calculate the field enhancement. So I guess that's something that people probably, I'm not aware of any literature that people have actually calculated how density of a state experienced by quantum dot, for example, changes with the thickness of the dielectric spacer, or even shape of the metallic nanoparticle, because shape can have a dramatic impact on it as well.
I don't know. Yeah, just for the is there any change of the radiation frequency when you increase the thickness of the
Radiation frequency?
Oh no, we didn't say any blue shift or red shift, anything like that. No, but in principle you should, because
so if the band structure change, so you will see the shift of.
But this is weak coupling. As I said, if these things happen when you start, for example, to go to a regime, the coupling becomes strong, moderately strong or so. The fact is that if it becomes very, very strong, then these two, for example, exciton-plasmon, coupling becomes strong enough, then splitting is happening quite much.
What is physics reason that the metallic structure will change the band structure of quantum dots?
Oh, the reason is that high field. You know, if you have, I'm sorry, yeah,
What field?
Electromagnetic field. The fact is if you have a plasmon, when you have a strong plasmon, the plasmon as a kind of resonance, let me put it that way. Plasmon is a resonance, like any other resonance. if you have plasmon as a two-level, for example, structure. You have quantum dot as a two-level structure. If these get coupled to each other, these two get coupled to each other through electromagnetic field, for example, then this splitting starts to happen. It's just like a kind of if you have two potential well, deep potential well, which have the wave function. But then if you bring them closer to each other, such that the wave function can see each other, splitting happen. Or better than that, if you have a two-level system and send a laser, but the laser is strong, even for single two-level system, one level gets split and becomes two, right? And the spacing, for example, radio frequency, this stuff, it becomes farther from each other.
That's when you have space overlap of the wave functions between the two systems. But in this case, you have your quantum dots with a certain band structure, and then you have gold or another metallic structure that are separated by silicon oxide. So unless you have light interaction, if you can go back to your one of the first slides showing the spontaneous emission rate.
Yes.
The one slide back. Yes, in that equation, I would expect a bigger effect from the edge, from the interaction part due to the plasma enhancement instead of changing of draw.
Yeah. Well, I have to clarify this. You know, when you talk about everything that I talk about and use this equation, I was in the regime, in the Wick regime. So I can enhance the field enhancement. I can increase the field experienced by the quantum dot by 10 times, 20 times. I'm changing rho, but not h, or h prime, or v. But if you spacing for changing h, the spacing should be maybe very, very small. You have to be the plexicon idea that people talk about that happens when the metallic nanoparticle and quantum dot are very close to each other. So imagine that if you have this, even assume that you have a two dipole. When the two dipole are very, very, very close to each other, right? Then the interaction between the two becomes strong, then the H starts to change. But that's not what we did. We are far, far from the case that H starts to change. When we use 10 nanometer, 50 nanometer of silicon, we are far, far from there. In fact, the idea of plexicon also happens when you have, like for example, if you have a tip of metal, which generates a huge metallic nanoparticle, huge field, and you put quantum dot right at the center somewhere, that it experiences a good coupling between plasmon and, remember, plasmon is a kind of generate its own field. Quantum dot generate its own field. So if they are close,
H is either E dot R or A dot P. So H is proportional to the electric field.
but this is not going to work for that. Oh yeah. If you think that this
Electric field usually enhance the H, right, or whatever you put in there, the dipole term.
you enhance the interaction between this regime is a linear regime. I'm not talking about the regime as those coupling that changes H is a nonlinear regime.
But H is proportional to electric field.
H is
Right.
proportional to
Yeah, so if you enhance the field, you enhance H. So you're changing H, you're changing the metric element.
But not the. You can enhance that, but you do not change the energy level. That's the point. You don't change the energy level. Energy level only start to change when the coupling is strong. Otherwise, yeah, you feel me, your interaction enhances, but the energy level, which he's asking about, that whether there is a shift or coupling between these, is not happening.
So thank you very much for your
You're
interesting
welcome.
colloquium.
Thank you.